During the Game Revolution series, I've been getting lots of helpful comments from viewers on how to do things better and faster. In particular, Bosco Retro has offered several great suggestions. Today we're going to go over 3 of those suggestions, and we're going to see if you can spot what the improvements are before I show them to you. Bonus. Ba-ba-da-ba-da-dee-dee. First, let's focus on this code here. As a reminder, what this does is it loads the U register with the current pointer into the gravel bytes. These are the source bytes that we're going to copy into the screen buffer. U is a pointer into these bytes. U starts here, and when U is here, we'll grab these 8 bytes. When U is here, we'll grab these 8 bytes. When U is here, we'll grab these 8 bytes, all the way until U gets to the end, at which point we'll grab those 8. Once U gets past here, we want to wrap it back around to the beginning. But the trick is that U is going up by 2 each time, and that's because we have 2 off-screen buffers. They're staggered with respect to each other, so each one is going up by 1 compared to the other, and thus it's going up by 2 compared to itself the last time that it was used. So within a single buffer, U increments by 2. We check to see if it exceeded those first 8 bytes. If not, we skip this line and go down here. Otherwise, we subtract 8. The idea is that if we wrapped around to here, we'll go back to here. But if we wrapped around to here, we'll go back to here. We just want to make sure that U is continuing to look at the appropriate byte, regardless of which buffer it's in. So when we need to do the wraparound, we subtract 8. And finally, we write U back into our buffer info. How can we make this faster? Pause and consider. Rather than gravel cur being a 2-byte pointer, why not have it be a 1-byte offset? We load a single byte register with the offset, add 2, and check out this fancy footwork right here. This does the wraparound if needed and nothing if not. If A is 8 or higher, this is basically taking the remainder when you divide by 8, which in this case is the same as just subtracting by 8. If A is less than 8, this is doing nothing. It's wasting a cycle or 2, but it's not having any effect. Store A back, and now we load U up at the beginning of the bytes and we offset U with the A register. So we're doing possibly some extra work here, but we're also saving work. What's the breakdown? The original way of doing things depends on whether we had to wrap around or not. If we had to wrap around, it would be 36 cycles. If not, we would subtract these 5 and it would be 31 cycles. The new way? Always 28. A definite win either way. Ba-ba-da-ba-da-dee-dee. Next, check out this unwound loop. What can I do to make this unwound loop faster? Before I show you the proposed improvement, it's probably useful to see what the cycle counts are if we do it this way. You'll see that we get a base of 5 cycles plus 1 more when we do these offsets, until we get to here. Now it's an extra 4 cycles. And if we scooch over to see what the actual instructions are that are generated, ED88, I assume, is telling us that we're doing a store D and we're using immediate offsets. And in particular, we're using only a 1-byte offset. But as soon as we go to 4 lines, now we need to use 2 bytes for our offset. And that costs us an extra 3 cycles each time. So if I want to keep this within a 1-byte offset as often as possible, I need to be taking advantage of negative offsets, like this. I get to go from -4 lines up all the way down to 3 lines down and stay within that 1-byte offset. Of course, I do need to make a quick change up here. When I originally set my X register to point, I now need to have it pointing in the middle of those lines that I want to be addressing rather than at the very beginning. So I had to add this 4 times 32. So if we add up our cycles for the old way, down to this line, it's taking 146. The new way, you can see we're taking advantage of 5 plus 1 over here for all of these. And then we move up to 5 plus 4 to here. And we get a total of 134. But then that begs the question, is it worth the overhead to readjust X between this line and this line so I can take advantage of 1 byte offsets for the rest? Now my code would look like this. I'm adding a brand new instruction I never had to do before. I'm adding brand new cycles I never had to spend before. But then that ensures that the remaining 6 stores get to use 1 byte offsets. Will it be worth it? Yes! We're now down to 124, even allowing for the fact that we added an extra 8 cycles. Because we saved 3, 6, 9, 12, 15, 18 cycles here. Ba-ba-da-ba-da-dee-dee. And finally, what can we do about this? This is the code that looks at the value that was written by the joystick reading code. JoyRx gets initialized each time through the main loop, and then we get to refer to it every time we want to know whether the joystick is left, middle, or right. If it's on the left, we branch here. If it's on the right, we branch here. If it's in the middle, that means it's 0, and we don't have to do anything special in this particular routine. So out of these 5 simple lines, can we make it even faster? Well, instead of having the convention that JoyRx is 0 in the middle, 1 on the left, 2 on the right, I could have a different convention. I could say JoyRx is 0 in the middle, -1 on the left, and +1 on the right. If I do that, I don't need these compares at all. Instead, I just load A with this value. I just do a branch less than for left, branch greater than for right. And again, if it were 0, we would just fall through. Doing it the old way costs us 15 cycles because we spent 2 and another 2 here for those compares. The new way is a total of 11 cycles, so we save those 4 cycles we spent doing the compares. Nice! Thank you again, Bosco Retro, for your suggestions. And thank you for watching.